Okay, we are going to start with section 3.6, part 2. And in this section, we're going to be going over absolute and relative error. So when we do numerical integration, we aren't finding the exact value of whatever we're integrating. So we have come up with a way to find the error. No. Okay. Alright, so for our absolute error is just going to be the difference between our estimate and the actual value. So if we say B is our estimate, A is our actual value, then the absolute error is A minus B, and just always take the positive of that, the absolute value, no matter what it is. The relative error is going to be when we make a percent out of it, or compare it back to the actual value. So we would do the difference of B and A, an absolute value of those, but then you would put it over the actual value A, so make an equation of it that way. If you multiplied it by 100, then you would have a percent of the error. So absolute error, relative error, a couple of different ways that we look at the error in numerical integration. Okay. Then let's look at example number 1. So for example number 1, this is using Simpson's rule. So use Simpson's rule with n equals 6 to approximate the natural log of 4 is equal to 1 over x, evaluated from 1 to 4. So if we look, let's just look at our regular integral of this. So the integral of 1 over x dx evaluated from 1 to 4 is equal to the natural log of x evaluated from 1 to 4, which is then the natural log of 4 minus the natural log of 1. And recall that the natural log of 1 is going to be equal to 0. Okay, so the actual answer to this integration problem is the natural log of 4. So we're going to now use Simpson's rule with 6 subdivisions to approximate what this integral equals. And then we will compare that to the natural log of 4 and see how close we are. So natural log of 4 equals 1.38629. Okay. So let's go ahead and set up our Simpson's rule and see what we get when we use Simpson's rule. So Simpson's rule, we're going to use S sub 6, since we have 6 subintervals, and then we are going to have 1/3 times delta x. So we need to know what is delta x. We're evaluating between 1 and 4, so delta x is going to be 4 minus 1 over n, which in this case is 6. So we get 3/6 or 1/2 is our delta x value. So we need to know what our endpoints are. So I'm just going to draw them out on here. So we're going to start at 1, and then our next one, there's your timer cannon. And then our next one's going to be at 1/2. And then another half is 2, 2.5, 3, 3.5, and 4. And that's going to give us 1, 2, 3, 4, 5, 6 subintervals. Okay, so those are all of the endpoints that we want to use. So 1/3 times delta x, which is 1/2, times f of each one of the subintervals. So f of 1 plus f of, so 1 is going to be the coefficient for our first one. 4 is going to be the coefficient of the second one. So 4 times f of 3/2 plus 2 times f of 2 plus 4 times f of 5/2 plus 2 times f of 3 plus 2 times f of 7/2 plus f of 4. Okay, so that's going to give us, oh, and then let's write out what f of x equals. So f of x is equal to 1 over x. That's the function that we are integrating. So f of x is equal to 1 over x. Can you go ahead and shut the doors on this? Turn it down. Okay, so just a reciprocal function. So we're going to have 1 over 6. F of 1 is going to be 1. For f of 3/2 is going to be 2/3. So we're just taking the reciprocal of each one of these. F of 1/2 plus 4 times f of 2/5 plus 2 times f of 1/3. Uh-oh, did I do 2 twice? Ooh. I have a 4, 2, 4, 2. This one should be a 4. I'm sure you've already caught that mistake, but I'm glad I caught it before I got to the end. Okay, and 4. So now here we've got 4, 2, 4, 2, back to 4 again, times 2/7. And then f of 4 is going to be 1/4. Why did I put f's in there? I shouldn't have kept putting f's in there, should have I? Okay. Let's rewrite that. We did fine after that point. Okay, let's try this one more time. So 4 times 2/3 plus 2 times 1/2 plus 4 times 2/5. I don't know why I got a little carried away with our function notation there. Plus 2 times 1/3 plus 4 times 2/7 plus 1/4. Okay, there we go. Much better. So when I went through all of this, I kept them all as fractions, and so that I could find my exact value. And so exact value on this one, I guess I didn't write it. I didn't write down my fraction, but my fraction was 1.38768. But I kept all of these. I did not put any decimals in for these values when I got this answer, so that I could have as close an answer as possible. Okay, so that is my answer that I get when I use Simpson's rule. Up here, when we found the actual integral, we got this answer of 1.38629. So if we want to find our error, okay, our absolute error, we're going to take the difference in those two numbers. So take the actual answer. Whoa. Let's try that again. 1.38629 minus 1.387698. And then we want the absolute value of that. So we don't care about negatives, how far off it is in one way or another. And then my error was 0.001408. That's my absolute error. If I wanted my relative error, I would take that number, 0.001408, and put it over the actual answer, which was 1.38629. Multiply that by 100, and I would have it in a percent form, which was a 0.1% error. Okay, so that's how we can use that absolute error and also the relative error. Okay, and that's what we are mostly going over. A couple more examples to go through, a couple more things. Okay, example number 2. We've got find the exact value of x squared dx, the integral of x squared dx from 4 to 8. Find the error of approximation between the exact value and the value calculated using the trapezoidal rule with 3 subdivisions. So this means that we need to look at both the real answer, the real solution, and the solution that we get using the trapezoidal rule. So first of all, let's go ahead and graph this. Now from 4 to 8, we're getting pretty high up there with our integral. So we're going to, or for our quadratic equation, so we're going to squash it down quite a bit. Okay, so let's just say that looks like that. Okay, so we've got to find the area under the curve between these 2 points. Okay, and it says right here we are using 3 subdivisions. Okay. And then we're using trapezoidal rule, so our trapezoids will look like this. Okay, so now let's go ahead and get started. We'll find the integral, the actual integral first. I don't know how to do this. I'll do it here. Okay, so we have the integral from 4 to 8 of x squared dx is equal to 1/3 x cubed of the integral from 4 to 8, which is going to be 8 cubed 1/3 times 8 cubed minus 4 cubed. Okay, which ends up being an answer of 149 and 1/3 is our answer for that one. Okay, so now we need to do the trapezoid rule. So for trapezoid rule, we need to know what all of our endpoints are. So our endpoints are going to be 4 and 16/3. Well, let's see here. Let's figure out, we need to know what our delta x is first. So delta x is 4 minus 8 minus 4 over 3, which is equal to 4/3. Okay, so I'm going 4/3 every time. So 4 plus is the first one, then 4 plus 4/3, and then plus another 4/3 is going to be 20/3, and then the next one is going to be 8. Okay, so between 4 and 8, that is what we end up with for our endpoints. So for our trapezoid rule with 3 subdivisions, we're going to have 1/2 times the height, which is delta x. So in this case, it's the width for our trapezoids. And then we're going to do 1 b sub 1 plus, oops, that one does need to be in, oh shoot, function notation. So 1 times f of 4. Okay, my video is going to cut off on me. We're going to finish this example up on the next video because there's no way I'm going to finish all this. Then times 2 times f of 16 over 3 plus 2 times f of Okay, we'll see you on the next